Pressure, pushing down on me, pressing down on you, no man has spoken.
For this experiment, you'll need a hot surface, a can of any shape or size, a preferably shallow bowl filled with ice water, and tongs.
Very still.
Are you ready?
Yep.
Here's an explanation of the experiment. So when you place the can with water on the heat source, it eventually changes phase from water to water vapor. So here is an arrow showing it changing to water vapor. So when it changes to water vapor, the molecules get more and more energy, which causes the pressure to increase inside of the can, since the expanding air is pushing against the walls of the can. As the water vapor expanded, the air that is inside the can is being pushed out and is being filled with just more water vapor. So when you use the tongs to flip the can upside down and place it on top of the ice water, the cold water causes the water vapor inside the can to condense. When the air condenses, the pressure decreases, which causes a partial vacuum. The pressure of the air on the outside of the can is greater than the pressure inside of the can, and so as the high pressure flows to the low pressure area, it crushes the can.
This project is called Dancing Raisins, and for it you need a glass filled with clear soda and a few raisins. Objects with a density greater than that of the liquid they're submerged in sink. This is why the raisins sink in the soda at first. The carbonated drink releases bubbles of carbon dioxide. The bubbles stick to the rough surface of the raisin and increase its buoyancy, causing the raisins to float. When the raisin reaches the surface, the bubbles pop and the carbon dioxide gas escapes into the air. This causes the raisin to lose buoyancy and sink back down. The raisins continue to rise and sink until the soda goes flat and loses the carbon dioxide bubbles. Buoyancy is the upward force exerted on an object submerged in liquid. The buoyant force is equal to the weight of the fluid that is displaced by the submerged object. The amount of liquid displaced does not depend on the weight of the object, but its volume. In the case of the raisins, when the carbon dioxide bubbles attach to them, their volume increases. The increase in volume causes the raisin's density to decrease. When an object is less dense than the liquid it's submerged in, it floats. The increase in volume increases the amount of fluid displaced, which in turn increases the amount of buoyant force that is acting upon the raisin. When the carbon dioxide bubbles pop at the surface, the volume of the raisin decreases and its density increases. Since buoyancy depends on volume and not weight, the decrease in volume decreases the buoyancy to the point where it can no longer hold up the mass of the raisin, and the raisin begins to sink. This process continues until the soda is no longer able to produce the bubbles of carbon dioxide.
For this experiment, you'll need an assortment of fruit and a clear pitcher filled with about 3.5 liters of water.
When the apples float, they are displacing an amount of water equal to its own weight. The apples float because apples are less dense than water, and according to Archimedes' principle, the apples are buoyed up by a force equal to the fluid it displaces. Our apples weigh about 7 ounces each, so the force pushing up on the apples to keep them floating needs to be about 7 ounces for each. If the force pushing up was not at least equivalent to the weight of the apples would sink. If the apples were to sit in the middle of the container and neither be floating or sinking, they would be neutrally buoyant. When objects' densities are equivalent to that of the liquid they are placed in, they will neither sink nor float. When you take an unpeeled orange and place it in a container of water, it floats. Unpeeled oranges are less dense than the density of water, because there are tiny air pockets inside of the peel, helping it to stay afloat. When you remove the peel from the orange, you are removing mass, but even though mass is removed, the inside of the orange has a greater density than water, causing the peeled orange to sink to the bottom of the container. When placing a lemon and lime in water, most people think that they would both float. Lemons and limes are usually about the same size and shape, but when it comes to floating, size and shape have nothing to do with what occurs when you place them into a container of water. If we were to take the time to calculate the exact density of the lemon and of the lime, we would find out that lemons are very close to the actual density of water, and limes have a greater density than water. This means that mostly all lemons will float in a container of water, and limes will sink to the bottom. The bottom line is that density plays a huge role in this phenomenon of lemons and limes.
There's like half your face and it's kind of funny. Callie! Sure.